Welcome to Khetz tutorials, and in this video I'll be covering a few things about nodal analysis. Now, you might have used some methods to solve circuits or to analyze and find variables in your circuit before, and nodal analysis is basically the same thing, but it helps you to find those same variables by using node voltages as your variables. So you start by finding the node voltages and then move on to find whatever value you might be looking for. So I can split this into two cases, or at least two cases. The first being, let's start off with a random circuit. Let's say something like that. What am I drawing? Okay, so something like that. So what you do in nodal analysis is you'd okay, let's add that and maybe that. What you do is you have to pick a reference. You have to pick a node which you can call 0 volts. So in my case, I'm going to choose this bottom one, 0 volts. Even if it's not clearly stated or it's not indicated, you have to choose a reference, and this is why. So if the first thing you have to do in nodal analysis, as it says in the name nodal, you have to know how to identify your nodes, right? So let's identify the nodes in this circuit. So here are my nodes in the circuit. I'm going to use a different color. I have a node there, I have a node there, and all of this is one node, right? So I basically have 3 nodes in this circuit, and I'm going to name these nodes. So this is, let's call this V1, let's call this V2, and let's call this ground, G and D, ground, which is the 0 volts which I chose. This is my reference node. So between that point and this point, I have a positive and a negative. That's how you can look at this. If you measure between that point and this point, you are going to find the voltage across that resistor. So this here is also V2. So if you have a node above a resistor and ground at the bottom, then you know that between those 2 points, you have V2, or the voltage which is above, right? So in nodal analysis, we are using KCL and Ohm's law. So Ohm's law says V is equals to IR, right? And now this V, like I showed you here, it is the voltage between 2 points. So it's between that point and this point, in this way. So at this point, we have V2. At this point, we have 0. So when we say V2 minus 0, it is the voltage between that point and that point. So now in nodal analysis, this is what we do. We say from one point or from one node to the other node and then divide it by a resistor value, which is in keeping with Ohm's law, which says I is equals to V over R. So all of this becomes a current because you're dividing the voltage between 2 points, or the voltage across this same resistor R, and then dividing it by R, which is that. So I is equals to V over R. So moving along to this point, let's label all of these. Let's call this R1, let's call this R2, let's call it R3, and this one R4. So now I want to form just random equations to show you how you do nodal analysis, or how you combine the formulas for each of these. So at node V1, we're now going to combine an equation at node V1. So the first thing you have to do is to identify the entrance and exit points which are connected to the node. At this point, we have 1, 2, 3 entrance and exit points which you have. So what I do is I like making my currents go out. So if it's not labeled, I like making them go out. So I'm going to have this rule which says when they go in the node, then it's negative. I assign a negative value. When they go out of the node, I'm going to say it's positive. They have a positive value, right? So in this case, looking at V1 or node V1, let's combine. We're going to have 1, 2, 3, because we have 3 points which are linked to this node. So we're going to have 3 terms in our equation. So doing that, we're going to say V1 finding the voltage. So what you do, like I showed you here, what you do is at the top, you find the voltage across the resistor which you're interested in. So we're interested, let's start with this one. We're interested in R1. So the voltage between, or the voltage across R1 is equals to V1 subtract this node. So this node is 0. So this is the same as V1 subtract 0 divided by R1. So that is the current which goes out there, right? Because I said out is positive in my case. I like doing that. That's what I basically do, right? So as you sometimes see in your textbooks and stuff, they don't really put the 0 because it's not really necessary. So you can just say V1 divided by R1, which is what I basically do most of the time when I solve my problems. So I'm also going to take this one as going out, right? I'm also going to take this one as going out. And now my points are V1 and V2. So between, or as I go from, this is how you can interpret this. When you're going from V1 to V2, this is how you move, right? So you put your V1, you put your V2, and then you put your negative sign to show that you're actually finding the difference, the potential difference, or the voltage which is across these 2 points, which is also the voltage which is across the R2. So you then say V1 minus V2 divided by R. And then I'm also going to take this one up here as going out, right? So I'm going to say plus because it's going out, and I said out is going out. So out is positive, and then I'm going to say plus. And so between these 2 points, or the voltage across the R3 resistor is V1 subtract V2. So V1 subtract V2, and then divided by R3. So those are all the 3 points which I have from the node V1. And then you can simplify this and then solve for whatever variable which you want. But we can't solve with just one equation. So we move on to find the equation for node 2. Node V2 or node 2. Now looking at node V2, we basically do the same thing. But in this case, I told you I like making my currents go out of the node. So in this case, we have V2 subtract 0 divided by R4, which is that current there, which goes down. And then we have that current which leaves the node, V2 subtract V1 divided by R2. So V2 subtract V1 divided by R2. And finally, up here, we have current which is leaving that node, V2, between V2 and V1. And that voltage is across the resistor R3. So I'm going to say V2 subtract V1 divided by R3 is equal to 0. Now you have two variables and 2 equations. You can manipulate these when you're given the values and find V1 and V2, right? So now let's say you had a variable here called Ix. My question is, what would you call this Ix? So if you look, you have a voltage V2 across that resistor, as we confirmed from this node which is above it. So this Ix is going that way, and it encounters the positive terminal of V2 first. So we can say Ix is basically equals to V2 divided by R4. Now, after finding V2, you can then come back here and plug in this value and find Ix. So you can apply this to any problem which you might have. If they ask you to find Ix, if they ask you to find any other variable, you just have to find a relationship between that variable and the node voltages. So that's how you do. This is the first part, and that's how you do it. Moving on to the second part of the tutorial. So now, let's say we have, I'm going to draw a similar diagram. Let's see, it looks like that. And something like that. You don't really care about what's happening in this side. I just wanted to show you that if you have a voltage source Vs, right, beneath a node, so this is the node, then this node's value is Vs. If you have a voltage source and nothing else, as you can see, there's no resistor here, there's no resistor, then the node above is equals to Vs as well. But if it were like this, you had a resistor there and the same voltage source Vs, then that would be a different case. That would be a different case if we were to call this V1 and this V2. So this is what would happen. To find the current which goes down here, you'd actually say V2 subtract Vs divided by whatever value is there of R. But in this case, you don't really have to do this because there's nothing there. So you just say that the node above has a value of Vs, whereas in this case, you can't really say that because there's a resistor in that path. Now, talking about voltage sources, before I move on to supernodes, there is one other thing you should know. So here's a trick. If you have a node here, a resistor, and let's say a voltage source, right? I'm going to show you two cases. In a voltage source here, and you have another node over here, right? So let's say you have something like this or whatever might be the case. Don't mind my circuits, just maybe focus on what I'm saying. So, right. Don't really care what's in the circuit. I just want to show you something. So let's say this is R, and then this is labeled as V. This is the voltage across that point and that point, which means this this node here is of value V. And then here, let's call this let's call this V1, and then call this one V2, right? So in that case, when I want to find the current which goes in that direction, I'd say V1. So it's going from V1 to that point. So you really have to go all the way until we reach this node here. So the equation for this, let's call it I. Whenever you have something like this, let's call it I. I is equals to V1 subtract. So you subtract all the voltage sources which you find in your path. And looking at the sign, you encounter this at the positive, so it stays like that. So it's going to be negative Vs, and then finally negative V2 when we get to this point, because we're interested in the voltage across the resistor, which is the voltage across these 2 points, right? So you include the voltage source and you include the node which you stop at. So it's going to be V1 subtract Vs subtract V2 and then divided by R. That is your equation for this current which goes in that direction through the R, right? Now, if you were at this point and forming an equation at V2, then this would be negative I, right? But for now, let's call it I1. You can just simply say I1 is equal to the negative of this. We should swap everything around, but you can also look at the voltage source and everything that's happening and do it as you go. So doing it as you go, you'd say V2 subtract. Now that you encounter the negative first, you'd say subtract negative Vs, and you'd say negative V1 divided by R, which is the same as V2 plus Vs subtract V1 divided by R. You could have gotten that from just negating all of this, which was going to give you negative V1 plus Vs and plus V2, which is the same thing as what we have here. So when you go in that direction, it's going to be minus minus. When you go in that direction, it's going to be minus plus. And that is how you deal with the situation where you have a voltage source in your path. So now let me quickly erase this. Then I'm going to continue to talk about supernodes. For the final section about nodal analysis, I'm going to talk about supernodes. So let's say we have a node here. Once again, don't mind my circuits. These are just random circuits which are mainly put together just to show you the concept. And yeah, so let's say there's V1 there, or let's say the label of this node is V1 and the label of that node is V2. Now we have a voltage source here of value, let's say 9. That's just a random value. Let's say we have a voltage source of 9. Now this voltage source is between these 2 points. And now what would you say is the current which goes through here? It's really unknown because V is equal to IR and I is equal to V divided by R. What is the resistance across this section? You don't want to assume that we have a short circuit or anything like that. So what you do is you basically transform this, or this situation is actually called a supernode. So what you do is you can draw something like this, which I like to do. You can draw something like that to show that this is one node. So these two nodes become one node because of this voltage source here. So now the relationship between these two and the node voltage is going to give you all you have to know about. So let me just complete this circuit so that I show you what I mean by that. So let's say this is R1, this is R2, this is R3, and this is R4. So now the first thing which you do is you look at the positive side of the voltage source, right? So on the positive side, you have V1, so that's what you start with. And then going all the way to the negative side, on the negative side, you have V2. So you're going to say V1 minus V2 is equals to 9. This is your first equation. And now for the second equation, instead of splitting these two like you would if there wasn't this voltage source or this supernode, you actually combine the equations of both sides and add them and equate them to 0. So let me show you how you do that. So you'd say on this side, you'd say V1 divided by R1, right? V1 divided by R1. Then you'd say plus V1 divided by R2. Then moving on to this side, you'd say plus V2 divided by R3 plus V2 divided by R4 is equals to 0. And these are your two equations, and you have two variables, and therefore you can solve for whatever you need. And this is how you treat a supernode. And that is all in this tutorial. I hope this was helpful, and good luck. Okay, so I almost forgot. If you had a resistor here of whatever value, then your supernode would actually, if whatever is in parallel with the supernode can actually be omitted. So this resistor value would be omitted, and all of this would be a supernode. So whatever you have parallel to a supernode becomes a supernode as well. So this resistor, because it shares these two nodes with the supernode, it would also be a supernode.